Good morning, ladies of calculus. Good to see you again. We're going to continue working on our limits graphically, and we may get into note card 2 today, but let's just go ahead with what we have here. So we have example 3, and you have this on your paper? Should have this, right? Because we finished example 2 yesterday, didn't we?
No.
We didn't?
do example 2.
We didn't?
No, we just, the bell rang.
The bell rang, so we just didn't quite get to 2. Okay, so, all right. Yeah, that's kind of snuck up on us yesterday. That's right. Let's go back to 2 then. Here we are at 2. So first, we have the limit as x approaches 1 from the left side, and what's that value of that limit going to be from the left side? Negative, looks like about -1, or maybe -1.2, something like that. We just call it -1. What about the limit as x approaches 1 from the right side? Positive 1. And then what's the limit as x approaches 1 of f of x? Okay, remember who wrote the if and only if thing up here, right? What does the if and only if thing say? That the limit exists if and only if
Wait, I'm confused now. So you feel like
pardon me?
the limit is approaching a positive? D and E.
Yeah, this is the left side limit. This is the right side limit. Are these two things equal to each other?
No.
No, they are not. So what is the limit as x approaches 1 of f of x?
Is that when you put the D and E?
That does not exist, that's right.
I'm a genius.
Okay, and what it is, the DNE, the acronym DNE includes the word does, and so this thing, it doesn't make sense to say equals does not exist. So you got to cross out the equal sign when you do that. Does that make sense?
Yeah.
Like this is a number, you would say equals 1, but you can't say equals does not exist. And what is f of 1? Might be kind of hard to see. What is?
1.
Looks like it's 0, right? Here's our.
Oh, yeah.
These are holes, and here's our point right here. So 0. And so this one right here is a good example of something that even if the value of the function exists, in this case it's 0, the limit does not exist in this case. Okay, let's go on to the next one.
So that's wherever the dark circle is?
Dark circle, yeah. And it's kind of hard, the graphics are kind of hard to see on this one, I will say that. Oops, went the wrong, there it is. This one right here, now we're at example 3. Limit as x approaches 1 from the left side is? Looks to be 1. And limit as x approaches 1 from the right side? 1. Are these two things equal to each other?
Yes.
Yes, so what goes here? 1. And what's f of 1?
1.
Yeah, this one here, f of 1, it looks like it doesn't exist. I don't know if how good the resolution is on yours, but this looks like it's whole, right? Yeah, so here's a case where you have a limit that does exist, yet the value at that point does not exist. So you can still have a limit even if that function at that point of discontinuity does not exist. Okay, next we got this one here. The limit as x approaches 1 from the left side is 1. Limit as x approaches 1 from the right side? 1. Limit as x approaches 1? 1. F of 1? -2. Okay, graphics are pretty good on this one. Is this very hard? Shouldn't be, but it's different, isn't it? It just takes some getting used to, I think. Okay, next we have this one here. The limit as x approaches 0 from the left side limit as x approaches 0 from the left side looks to be 1. Limit as x approaches 0 from the right side 1. Limit as x approaches 0 1. F of 0. Do you see any kind of hole there? No. What is F of 0?
Oh, so it's still be 1?
Yeah, there's nothing that tells me it does not exist. I don't see anything.
So if it's an open circle, then it doesn't exist.
Right.
No solid.
Yeah. So we're going to, so next one, example 6. Limit as x approaches 2 from the left side. Okay, we're approaching 2 from the left side. What's our limit here? Okay, this is what? What is this thing right here? Almost. It's a vertical asymptote. Okay, and so what is the limit as x approaches 2 from the left side? Yeah, it does not exist. So this does not exist. And in this case, it does not exist in a particular type of way. It does not exist in that it approaches infinity. The function approaches infinity. So approaches, because there are different ways a function cannot exist. As limit as x approaches 2 from the right side of f of x also does not exist. And in this case, what are we approaching here? Negative infinity. Does not exist, and does not exist in the manner of approaching negative infinity. And the limit as x approaches 2 of f of x does not exist. What is f of 2? Does not exist. And if you could graph this in a calculator, what are you going to see when you go to table view and see where x equals 2?
Error.
You see an error or undefined something, probably error. Calculator you got. Okay? Okay, example 7. Limit as x approaches 2 from the left side of f of x is? Does not exist. Yep, pause infinity. And limit as x approaches 1 from the right side? Does not exist. Also pause infinity. Now, what about this one? Limit as x approaches 2, a negative 2 of f of x. What is that going to be? Yeah, it's kind of, they look like they're the same, right? But these things aren't really numbers. So even something like this, where the function does not exist in the same way, still the limit does not exist. And f of negative 2 does not exist. And this one here, it's the same thing except for what?
The negative 2 is going to be a negative.
Yeah, so this will be f of negative 2, yeah, it looks like 0, right?
Yeah.
Yeah. And everything else is the same. Okay? Let's see. Okay, that's the limits. And then that's the homework. I'm going to give you a homework assignment. But we're going to go right to note card 2. I'll give you one homework assignment. In fact, I'll have you take it home and you can bring it back. And that's going to be, these are pretty easy, right? The homework assignment is going to be really easy. It'll be easy enough to do it while you're waiting to play volleyball even, right? No, no. Okay. Now we're to note card number 2, analytical strategies for finding limits. Okay, step number 1, try direct substitution. If that doesn't work, you try to factor and then use a cancellation technique. And finally, number 3 is special trig limits. And this is something that you just, this thing right here is something you just have to remember. And we're going to see examples of it. So let's go ahead and look at examples of this. So we go here and we see, okay, that one's reserved for trigonometry. And these ones that says has a blank reserved for trigonometry, we're going to cycle back through that later when we do trigonometric functions. But number 2 is what we have here. And so what is step number 1 to try?
Direct substitution.
Direct substitution. And so we'll say equals limit as x approaches 1. And you would say, and actually you can try just to substitute directly, and you're going to put in 1 squared plus 5 times 1 minus 6 over 1 minus 1. And so what do we have here when we simplify this? 1 plus 5 minus 6 is what? 1 plus 5 minus 6 is 0.
Over 0.
And 0 over 0. Okay, whenever you have 0 over 0, this is called the indeterminate. And I'll show you what happens that means. What this means is it means more work. That's what that means. You have more work to do. Okay? So that means that step 1 didn't work. And what is step 2? It says try what? Cancellation. Factor and cancellation. So let's go ahead and do that. Now, if you get to the point where it's 0 over something, then the answer is 0. Okay, 0 over a number, that's 0. That's not more work. If you get something over 0, some number over 0, what's that going to be? Undefined. And that's also not more work. The more work only is required if you come up with 0 over 0, which is called the indeterminate relation. Okay, so let's try to factor and cancel. So So if we're able to cancel, what is one of the factors of this thing here going to have to be? Yeah, so one of the factors for this thing to be cancelable, we know that one of these factors has to be x minus 1. Because that's the only way we could possibly get 0 over 0.
The other one is x plus 6.
Yeah, so x plus 6.
Oh, yeah.
Let's see what it is, because that's minus x and plus 6. So that's it. So does this thing cancel? Yes. So now, if we substitute in 1, what do we get? 1 plus 6,
7.
which equals 7. So our answer to this one is 7. All right, I want to talk about, I want to show you graphically what's happening here. So what happens, we have this x squared plus 5x minus 6 over x minus 1. So x squared plus 5x minus 6 over x minus 1. So we graph that. So the graph looks like this. All right. And we're trying to find out where x equals 1. And so what is that going to look like? Well, where x equals 1, that's what we have here, right? But on the graph, we look at the graph, at x equals 1, what does that look like? It looks like 7, doesn't it?
Yep.
So what this is what kind of thing here where x equals 1? What do we call that thing?
Intersect.
No. What do we call that thing? What do we call that thing?
Point jump.
Removable discontinuity.
You're really far away for me to be able to read that.
Yeah, it's a removable discounting, but I told you the t-shirt was wrong, didn't I?
Yeah.
Yeah,
It's your new
Danny mixed it up. Yeah, it's a hole though, and a removable discontinuity, or a point discontinuity. Point discontinuity, which is a hole, which is a removable discontinuity. That's what that is. You were reminding me to talk to Danny. I think I'm gonna have to go over, I have to get that file out of his computer and get him to erase that file. Okay, next. Okay, this one here, if a is not equal to 0, then limit as x approaches a of this thing is, and we'll see if you can work. If we plug in a, what do we have here for x?
0.
We have 0 over 0, right? Because if you plug in, if you put x goes to a, then you have a to the 4th minus a to the 4th, and you have a minus a. So that's more work, right?
Yeah, that makes sense.
So what you have to do is factor and cancel. Well, how do you factor this guy out here? So I want you to try to do that for a minute. This is one, I'll tell you that, yeah, this is one that every year,
I feel like you're saying
I don't know what
stuff,
trick it is.
but you're not like,
Teaching.
you're saying stuff that doesn't make sense in my brain.
Yeah.
doesn't
Like I
it?
need to see you do it for me to understand. Like you're saying these words, but it's like a foreign language.
Yeah, like I don't know.
Like you gotta
It's like
teach
you're
me what the
speaking
words
Spanish.
are. before you say the word.
Like we need to
I
do
don't know.
definitions.
Definitions,
I wouldn't say
okay.
definitions, but
I would need definitions.
Okay,
like what you're
That's good to
saying,
know.
this is like a foreign language. And I don't know what you're,
like,
like it was tough to like work it through, like, and we would know like every part, like what every part meant. You teach it to where I don't even know what you're talking about. And like.
okay, now what words have I said today that you didn't understand?
What is language? What is that?
Because I need some specificity, because you're telling me, okay, you're speaking a language I don't understand, well, what is the word that I said that you didn't understand?
Just like all of it, like you put it together, it just doesn't make sense. Like, you said, tell us to like do it, but like, I don't know what I'm doing, so I can't do it.
It says factor. That's what it says, factor. They give you factor the denominator. Factor to the denominator. You know how to factor a denominator? You know how to factor something?
Yeah, the last one was easier to factor. 'Cause it was
Yeah,
the
that
numbers.
is, I agree with that.
No, I just didn't know
Okay, I will
how
tell
to
you,
factor
I'll tell you
it.
something, the denominator you can factor using a technique we talked about. Difference of squares. Remember we talked about difference of squares? You can factor using difference of squares.
I don't remember what that is.
No? Okay, I'll give you an example.
Are we talking about like the square we did?
A squared
Parentheses with X, like X minus A, and then you have to find the other one, and you put the.
Okay, this is factoring a difference of squares. And you'll see it a lot of times if you had like x squared minus 9, that would be like x plus 3, x minus 3.
So it would.
So when you're factoring this one, is it gonna make them squared and then you go even farther than that?
Yeah, yeah, that's what it is.
So
Yep.
it would be like 4
X minus
X
times
Yeah.
X minus
So you have to kind of use an extension of that.
So it's 4X minus X.
So here we'd have x minus a. And down here, you'd have x squared minus a squared, and then x squared plus a squared. Can you factor this further?
Yes.
Yeah. So let's do this.
And then you just do it 4 times?
X minus a, x plus a, and then you just have x squared plus a squared.
So you don't have to factor the other one?
Pardon me?
You don't have to factor the other one?
Yeah, this thing right here, if you have a sum of squares, that's unfactorable. Okay, that's unfactorable. So we can't do anything with this. We can't do anything with this.
X
But-
third plus.
So what happens now?
Q plus A Q.
You can just
Yeah,
cross those
cross
out.
out.
Cross out.
X minus A, not X.
And so now you're going to plug in what? A.
So you're just gonna put those together, it's gonna be
You're
X
adding
cubed,
it,
so
so- It's A plus A and then A squared plus A squared.
Yes.
Yeah, that's what I was thinking. So it'd be like.
So that's going to be 2a. So it's 1
6.
over 2a times, is that 2a squared?
Yeah.
So what is that going to be?
4, 6.
1 over 4a cubed.
Yeah.
So that's our answer, 1 over 4a cubed.
That was fun.
Yeah, it is.
The X I don't.
Now this one here, this one right here, I want to show you something. I want to show you a feature.
Where'd the X's go?
The X turns into A, so you plug in all the.
Yeah, you replaced. When you did it first, you got 0 over 0, so you had to keep on going. Now you know what these asterisks are?
No.
Whenever you see an asterisk, that means that was an actual AP test problem. And this one here, I think this one here might have been actually a little bit more of a challenging AP test problem.
Yeah.
But that was an
Hopefully
actual.
that was kind of easier if it was like numbers and wasn't just letters.
Now, fortunately, most of the ones we have in this class are going to be like problem 2.
Yeah.
Okay, you'll see something like this again, probably, but not as often.
Don't erase, don't erase, don't erase.
But just realize that you'll be able to factor it. Another thing we're going to do is we're going to have techniques of limits. There's another technique beyond this that we're going to cover later on. It's called L'Hopital's rule. So that's something to look forward to being able to do. L'Hopital's rule.
Go back, I can get all that copy back.
You didn't get this? Okay. It's just factoring, that's all that is. But to me, one thing I think is challenging about something like this, correct me if I'm wrong, is that having that, if it was like x to the 4th minus a number instead of a to the 4th, it might look easier for me to do.
Yeah.
That's all. But you see a lot of things here that are pretty, how should I say, I forget what we call this thing, abstract. That's the word I'm looking for. Okay, let's go ahead to this one. Okay, this is another type of problem. It just looks different. This thing right here is a type of function, and I don't remember if we talked about this last year, but if we did, we didn't talk about it very much. What kind of function do we call this? Do you remember? No? Okay. Whenever you see a function like this that has like f of x equals, and you have different lines, you call this thing a piecewise function. Piecewise function. So basically what you have is you have different rules for different pieces of the function. And so what this says here, and this is not written like you normally see it. Usually you'll see a comma here. And what this says is that the value of the function is 2x squared minus 3 when x is not equal to negative 4, and x is equal to 1.7 when x equals negative 4. So this top part applies to everything that is not negative 4, and this thing on the bottom part applies to when the thing exactly equals negative 4. And so to find the value, to find the limit, where are we going to try to substitute in negative 4 to figure this out? For x? Up here? All right, let's do that. If we plug in negative 4, 2, here's negative 4 squared minus 3, what's that going to be? I think it's 29. It looks like 29 to me. And that's a PEMDAS problem, right? We talked about a PEMDAS at the beginning of class, didn't we? So 29 is it. And so what is the limit of this thing right here? What is our answer for this? Our answer is 29. Does it matter that at x equals -4, the thing is 1.7 and this is 29 here? No, it doesn't. Remember, it's this. We had -4 and the function's going right up here to 29. What happens here? We have this, right? We have a hole, and where does that value show up? Right down here. So there's the value of 1.7, and this thing is a hole, and so the limit does
No, it exists.
exist,
It does exist.
right? Because we have left-hand limit equaling right-hand limit.
Oh, yeah.
Limit does exist. But the value of the function itself does not exist at that point. Okay? Piecewise function. We're going to be able to, we do a test for continuity, we'll do that.
So for this homework page, we'll be doing it tonight?
I'll give it to you, yeah. And what it is, it's from your text, but I'm just going to give it to you on a separate sheet of paper so you can work it out. And it should be really fast to do.
Can we take our binders home though?
You could. I don't know if you really need to for this.
Like a reference?
Yeah, I don't know if you need to for this. Let's see if I can find it.